Welcome back. In this video lesson, we're going to investigate satellites that orbit in a circle, and we'll try to come up with some expressions that help us calculate what's the speed, angular speed, period of orbit, and acceleration due to gravity, or if we want, we can call that the centripetal acceleration of our satellite, all as functions of the distance of the satellite. So the distance I'm referring to, the value of r, we can represent graphically. So r just represents how far it is from the satellite's orbit to the center of the object that it's orbiting. So let's draw in our satellite. The satellite has a mass of lowercase m, and then the object it's orbiting, in this case the Earth, has a mass of capital M. So there's just a few equations we need to derive these formulas that we're looking for. Centripetal force is mv squared over r, and we can obviously apply the idea of centripetal force to this problem because the satellite is an object that's moving in a uniform circle. Gravitational force, so this is governed by Newton's law of universal gravitation, g times the mass of the satellite times the mass of the Earth divided by r squared. And then if the velocity changes only in terms of its direction but maintains a constant speed, a constant magnitude, then the value of that tangential speed is just the circumference of 2 pi r divided by the time it takes to make one complete orbit, which we call the period of orbit, symbolized by capital T. So by equating these expressions, we can derive a few simple equations. Now, I think in the previous video we already showed that acceleration due to gravity is certainly a function of r. So if force of gravity is g mm over r squared, but force of gravity is also mg, then when we set these equal to each other, the m cancels out, and gravitational field strength is nothing more than capital G times the mass of the planet being orbited divided by r squared. So it's following an inverse squared relationship. The gravitational field strength is the object's centripetal acceleration. So these two expressions mean the same thing. If you were to graph it, what's the centripetal acceleration of a satellite versus distance? In other words, if we take the satellite and move it to a higher orbit, would its acceleration be more or less? Well, certainly less. Acceleration is inversely proportional to r squared. The minimum orbital distance is that of a treetop orbit, where the orbital radius and the planetary radius are one and the same. So it doesn't make sense to have any data plotted in that shaded region of the graph. For the Earth, the centripetal acceleration of a treetop orbit would be 9.8 meters per second squared. And from there on, the graph follows a proportionality to 1 over r squared. So let's see if we can derive the expression for velocity as a function of r. We might have done this in a previous video as well. If we set gravitational force gmm over r squared equal to centripetal force mv squared over r, m cancels out, one of the r's cancels out, v squared is gm over r, so the speed has to be equal to gm over little r. Now if we want the speed of a treetop orbit, in that case the orbital radius is the planetary radius. So for the treetop orbit, it's the square root of gm over capital R. But that's a special case. This is the more general form of the equation. And if you were to graph that, again, the lowest possible orbit is a treetop orbit. So no point showing any part of the graph within that shaded region. And we found earlier in a previous lesson that for Earth, the speed of the treetop orbit is about 7,900 meters per second. And we see there's an inverse proportionality. The speed is proportional 1 over the square root of r. So the speed decreases the farther away the satellite gets. However, it doesn't drop off as radically as the acceleration value because it's not a 1 over r squared proportionality. It's a 1 over the square root of r proportionality. So you have to be careful not to confuse the symbol capital R with lowercase r. And furthermore, let's not confuse that with the symbol h for altitude. In fact, there's a relationship between all these variables, right? If I add h with capital R, the altitude with the planetary radius, that's equal to the orbital radius. If the satellite orbits around in this circular path, not only does it have a tangential speed in meters per second, but we could express how far it travels in a given time interval. So let's say it goes from point A to point B. The magnitude of the velocity doesn't change. The direction does. The object has traveled through an angle of theta. Omega is d theta dt. The relationship between angular speed and linear speed, v is 2 pi r over t. Omega is 2 pi over t. So simply put, v is just equal to omega times r. So omega is equal to v over r. And we just found in our previous derivation that v is the square root of gm over r. So the square root of gm divided by r, all divided by r, or in other words, divided by the square root of r squared. So we have omega is equal to the square root of gm over r cubed. What about period as a function of orbital distance? So if a satellite orbits barely above the surface of the Earth, in other words, back to this idea of the treetop orbit, I think we've expressed in a previous video that that period is about 90 minutes. And that's roughly the orbit of the International Space Station. The International Space Station doesn't just clear the treetops, it orbits at about 200 miles above the surface of the Earth. But 200 miles when compared to 4,000 miles isn't really all that much. So for all practical purposes, the ISS is very nearly a treetop orbit. So what should be the case of a satellite that orbits at a higher altitude? More time or less time? Yeah, the farther away it gets, the more time it should take. For one thing, we've already seen that the farther away it gets, the speed decreases, and as the speed is decreasing, the path it has to follow is increasing. So there should be a profound effect on a period as a function of r. So let's see. We just derived omega is square root of gm over r cubed, but we also stated that omega is 2 pi over t. That means omega is expressed, what we really mean by 2 pi is 2 pi radians. That's the angular displacement for a full circle, right? So omega is units of radians per second. So let's see. 2 pi over t, that's one way of saying omega, but omega must be equal to the square root of gm over r cubed if we square both sides of the equation, we get 4 pi squared over t squared is equal to gm over r cubed. So let's do some cross multiplying, or let's invert both sides of the equation. So we'll do 2 steps. We'll invert both expressions, and then we'll have to multiply both sides of the equation by 4 pi squared to cancel it out. So let's do 2 steps in one. Period squared would be equal to 4 pi squared r cubed divided by gm. So let's take the square root of both sides as a final result, and we can state that the period is equal to 2 pi times the square root of r cubed over gm. So this suggests a proportionality we haven't seen much before in any previous unit of study. So we've seen a lot of cases where one quantity is proportional to another one squared, or maybe a quantity is proportional to the square root of another quantity. Here we have a case where the quantity we're interested, the time it takes to complete one orbit, the period of orbit, has a proportionality with r. So instead of stating the equality, we just state the proportionality. Period is proportional to orbital radius to the 3/2 power, right? We've got radius cubed, but then we're taking the square root of that. Okay, so what's that suggest if we make a graph of period versus orbital radius, and one more time make the point that there's no need to graph anywhere within that shaded region. So let's start at about 90 minutes. So this is a graph for the case of the Earth. Yeah, the smallest possible period is that of the treetop orbit. And from there, as r goes up, period also goes up, but it's not a 1-to-1 ratio, right? Period is not simply proportional to r to the first power, it's proportional to r to the 3/2. So this curve is concave up. And something interesting we could ask is we can say, where would this curve intersect a period? What would the orbital radius have to be so that the curve intersects a point on the time axis of 24 hours? Think what that would imply. Let's say you were standing right here on the Earth, somewhere near California, and the satellite at one moment in time is directly overhead. Well, the period for the Earth's rotation is 24 hours. So in, let's say, what's 1/4 of that? In 6 hours, you're going to rotate about to here. In 12 hours, you're going to rotate and be standing over here, right? 6 hours, 12 hours, 18 hours, and you'll come back to where you were in 24 hours. That's just the way the Earth rotates on its axis. The satellite, if it also had a period of 24 hours, then it would follow the same description. In 6 hours, it would still be directly overhead. In 12 hours, it would be directly overhead. The satellite would be locked in step with the orbit of the Earth. Now, it really wouldn't work out this way. I've drawn it as if the Earth is rotating about an axis that doesn't really agree with its rotational axis, right? I'd have to draw this picture differently. The axis of rotation is here. So I suppose I should really imagine draw the equator. And so instead of a person standing here, I should say picture somebody standing on the equator. Can you see that? Let me use a different pen color. There. Figure not drawn to scale. And then in 6 hours, that person is standing here. In 12 hours, they'd be somewhere we can't see them, back on the other side of the Earth. In about 18 hours, we can see them start to poke out over here. And in 24 hours, they'd be back in this position. So I should really be imagining a satellite that's orbiting in a different plane, right? Or orbiting somewhere out here. And the question is, how far away from the center of the Earth would that orbit have to be so that the satellite is locked directly overhead? There's a name for those type of satellites. Because they keep time with the motion of the object on the Earth, we say they're synchronized or synchronous. And because they're synchronous with the Earth, we say they're geosynchronous. Another word you could use is geostationary. And so the geosynchronous satellite is one with an orbital period of 24 hours. Maybe in a next video lesson, we'll mathematically see if we can calculate what the value of r has to be for the geosynchronous satellite. Okay, thanks for watching.